This is the demo of the Graphs and Topology for Chemist package, which is GandT on GitHub, which implements persistent homology features for chemistry machine learning problems. Now, the sort of chemistry problems that this is useful for are things such as molecular design, which is of great use to humanity. For example, it's used in drug development, developing new materials, biotechnology, biochemistry, and so on. There are a few problems with chemistry machine learning that are specific to that field. For example, how best do we input the three-dimensional structure of the molecules? There are various different approaches, but for the three-dimensional structure, most people use the grid featureizer, which is very sparse and large data and very difficult to train from. Chemistry datasets are also very, very small compared to the sort of datasets that machine learning normally works well with. Therefore, we really must get the best out of it. To approach this problem, I looked at the field of persistent homology, which is a brand new area of topology. Topology is interested in counting the number of topological features in a surface, and persistent homology applies this to point clouds. The way it does this is it puts a ball on each point and slowly grows the radius and counts the number of topological features. The sort of features we are talking about are flat 2D rings or flat 2D holes surrounded by a ring, or 3D voids, which is a hole at the centre of a football, or connected regions. So in this example with benzene, when the radii of the ball are very small, we have 12 connected regions. That's 12 points. They're not connected to each other, they're connected to themselves. As the size of the balls grow, they start to merge, and as you can see, we now have 6 connected regions in this example, and if they keep growing, eventually they merge into a loop, which is one connected region and one loop. This will give us the PHF featurization, which is very, very small, and thus we can use incredibly simple architectures in order to solve these problems. For example, all the neural networks in this study are 2-layer feed-forward neural networks, which is one of the simplest available, of 100 units per layer or 50 units per layer. One of the most difficult problems in biochemistry and drug development is the protein binding problem, where you want to find how well a drug molecule or ligand binds to a protein binding pocket in order to develop. Applying this method to the difficult problem of protein binding, we get very encouraging results. For example, the state of the art on this problem, which is 2015, is a graph convolutional neural network, and we see that the PHF equals it in terms of how well it solves the problem. However, using PHF, we can do this in 5.5 minutes on a neural network as opposed to 1.5 hours for the graph convolutional neural network. The plot at the bottom shows using PHF features and combining them with a couple of easy to calculate chemical features, and we are commensurate with the state of the art and statistically indistinguishable from the best of the state of the art on this problem. Another dataset that's very important for drug development is solubility, also known as the Delaney dataset after the guy who came up with it. And we can see here, comparing to the state of the art, we equal the state of the art using PHFs. However, these are all neural networks, and you can see that the neural networks for PHF are many, many, many times smaller. Taking some of these models and actually running them on a home computer, I was able to compare the time taken and energy usage to do these studies. And as you can see, PHF solves the problem in about 30 seconds, as opposed to 18 minutes or almost 2 hours for some of the other models, and is many, many times more energy efficient. So the Graphs and Topology for Chemistry software, which is GandT on GitHub, is able to take in molecular structural data in .mol, .pdb and SMILES formats, and is able to make persistent homology feature datasets. These can be used directly, or you can use some of the examples in this project in order to do some training. Our first example is the analysis of persistent homology for molecules notebook, which will make some of these concepts clear. So we have some SMILES strings, which are these data here, and we're going to look at benzene. This is the molecule. The first thing we do is we make a point cloud of benzene structure, and here it is. So you can see there is a loop here, a hole in the middle of benzene, and it's relatively flat. Then we make a persistence diagram. Now what these do is they track the number of connected regions, H0, and the number of flat 2D holes, H1, or rings, and the number of voids, 3D voids, which is H2. What we do is we put a ball at each of the points and slowly grow the radius around the ball and see where these features merge or are born and die. So at 0 angstroms we have 12 features which are born, which is the 12 atoms. At 1.1 angstroms, 6 of them die, which is the CH bonds merging together, or merging from the atoms. At 1.4 we have another 5 features that die, which is the carbon-to-carbon bonds, and the remaining connected feature is the one that covers the entire molecule. At the same time that the bonds die, they merge into a ring, a new feature is born, which is the H1 feature, which is the ring, the 2D hole at the center of benzene. Now in persistent homology, the most persistent and most important features are the ones that are furthest off this line. So in the language of persistent homology, benzene is mostly a ring, a 2D hole, which is made up of smaller connected regions, which is similar to how a chemist might think of it. Another example that will make a lot of these concepts clear is the buckyball. So the buckyball has a void at the center of it. So this is what we mean by these sort of 3D holes, if you can see that as I move it around. And it also has flat holes, which are the hexagons and pentagons made of carbons on the surface of the buckyball. So when we do the persistence diagram, we see the most persistent feature is a H2 feature, which is the void at the center of the buckyball. We also have some H1 features here that are pretty persistent, and those are the hexagons and the pentagons of the surface, and we also have 2 sets of bond lengths there. Now we're going to look at a slightly more complicated example found in the testing PHF datasets, which is the protein binding problem, and we're using the 2016 version of the data. So first we have a look at some of the files. As you can see, we can load the protein binding pocket and the ligand into these molecule objects. And these aren't just pictures, because we also have the coordinates of the atoms and the atom list. As before, we create a point cloud, and this is for the protein binding pocket, and perhaps you can see there is a void in the center of it where the ligand would sit. We then plot the persistence diagram. It's much more messy than the buckyball, of course, but we do see that the highest ranking feature that's most persistent is void, as expected. Do the same for the ligand, which is not dissimilar from benzene in terms of its structure, in that it's flat and has a loop or ring. And again, it's not surprising we get a very similar persistent diagram to benzene, with one of the most persistent features being the H1 ring at the center. But we don't actually train from these data. Instead, we convert it to a vector so that we can use a one-dimensional input and thus one-dimensional neural networks, for example, feed-forward neural networks, which are some of the simplest ones that you can get. And we calculate these things such as persistent entropy, and the details of those are given in the manual. GandT includes a method to make data sets. You put your data set here with your small strings and any other information you may have, and then you'd want to use these scripts here. For example, for the Delaney data set, we run this. What it does is it reads in the molecules, featurizes them one by one, and then writes them out as CSV files, the data that is, which can be used immediately. And then you can add in extra data that you may have, which is perhaps non-structural, and add that into the HDF5 file, as you can see has just happened there. Here we can load in the HDF5 files that have been pre-featurized for you. We've got 2 for the protein binding problem, the larger data set here, which is called refined, and the smaller one, which is never trained on, which is used as a test. We can interrogate these data sets. For example, this is what we're trying to predict, which is the binding energy. And we can quickly put them together for training in this notebook. As you can see, we've got 18 features for the protein and 18 features for the ligand, which we've stuck together to make a vector that's 36 numbers long. And this is an incredibly small and compact featurization. We have a training set of 4,500, and the core data set is 284. Now we're just going to train a random forest, and you'll see it's very, very quick. There we go. And here we go. We've got the R squared here. We get 0.9, so it has trained well. Our test set gets about 0.6, and our holdout set, the generalization data set, the core data set, gets about 0.46. These numbers do change, which is why it's worth running repeated experiments, and there are examples of how to do that in the experiment directory. Alternatively, if you want to combine data sets and do slightly more in-depth experiments, please look at my GitHub because I have other programs and software to do that. To conclude, we find that using persistent homology features, we are able to equal the state of the art for various chemistry problems, and we do this in a very efficient way that is much faster and cheaper. For example, we can take up less space on the disk by featurizing, as you can see on the first line. It is also many, many times faster for training protein binding problem, which is a difficult problem. And when we measured the energy efficiency by rerunning other people's algorithms on the same computer, we find that the PHF is many, many times faster and much more energy efficient. For more information, see this paper, which will be coming out shortly and should be up on arXiv in the next month, or look on GitHub for the code. Thank you.